This is Statistics 243 for Monday, November 24th here at Berkeley. Okay, let's go ahead and get started. Okay, so the plan for today, I want to pick up with the EM example, which we didn't quite get through, which I was a little bit disappointed about last time. I thought I was going to get all the way through it, but actually it's probably good because I think it's a good thing to see a couple times. So we can go back over the initial, the idea is I'll go back over the initial notation, clear up the thing that I was confused about last time, and then we'll see the maximization steps as well, at least in sort of sketch form. Okay, so remember what we were doing was we had this normal mixture as representing the distribution of the x's, and we introduced this latent variable, one for each of the observations, which was the z, which gave us the information of which component the observation belonged to. And the idea is that if you knew that z, it would actually make the problem quite a bit. It would make the problem quite easy, because then you could just group the observations and figure out what the parameters were for the component, for each of the given components, knowing the observations that belong to that component. Okay, so to go back to where we were, we had written out this. Here I'm doing it summing over all the i's. I've already taken the log of the likelihood, but the individual pieces are, I've written out the log likelihood as the joint distribution for x and z, for the observed data and the missing data, so for the complete data. And I'd written it out in this factorized form, so I had the marginal for z and the conditional for x, d, and z. And so then I said, okay, we can write that out. It looks like this. Here's the marginal for z. Here's the bit about if we know that zi is equal to k, then we know that it comes from the kth, in this case, a normal distribution, although I'm being sort of generic here, just saying f sub k. Then the thing that I got confused about last time was this business of taking the log over here. And so what's going on here is this is a sum, but only one of the terms in that sum is non-zero. And so what's going on here is I'm going to just move the indicator out and say, and therefore this is just now still going to be an indicator, but it's basically going to say which of these pieces is non-zero. And so I've got the log of this product here. And then of course, once I have the log of the product, I just have the sum of the log of the two log pieces here. So this is just sort of recognizing that it's awkward to deal with the indicator function, but because of this representation where just one of the pieces is non-zero, I can do this manipulation and basically move the indicator outside here. Okay. So then what we saw last time was, okay, we have the log likelihood in terms of the complete data, and now I want to take that expected value. Sorry, I should go back to the PDF here. Now I want to take this expected value here. So I've written out log of theta given y. I'm sort of here I'm writing it as a function. I'm writing it as the likelihood function of theta, but there I've written it out as the density for the complete data. And now I need to take this expected value where I condition on the observed x's, and I'm basically making use at the current iteration of the current value of the parameters at the tth iteration. So then I am, when I think about taking the expected value of this expression here, the key thing, one of the key things to remember is what's random that I'm taking the expectation with respect to. And I'm taking the only thing that's random in here are the z's. So this just becomes, I'm taking the expected value of this, the expectation gets passed inside the two summation terms. The expected value of this product, this is a constant, so that basically just comes out of the expectation. So this is just the expected value of z equals k, but under the conditions that I stated here, given the x and given the theta t. So I've just put in the xi, because the observations are all conditionally independent of each other, so that the other x's don't matter for the sake of this particular zi. And then I've explicitly written out what are the parameter values that I'm going to use in calculating this conditional probability. I'm going to use that mu k is equal to the current value of mu k, so the tth one, the same for sigma and the same for pi. Okay, so that sort of basically recap most of the way that we got through last time. Are there questions that anybody wants to ask at this point before I go to the next step? Oh, right. So pi k is just the marginal probability that zi equals k, and pi kt is the probability that zi equals k, basically given that the parameters that I'm using are the parameters of the t iteration. Okay, other questions? Okay, so if I looked at this, we described this last time, if I see that I have z given x, well, I already have terms that involve x given z and marginals for z, so I can just think of finding this via Bayes' theorem. And if I do that, I'm going to get the marginals for z, and then the distribution of x given z. And so if z is equal to k, that tells me that I need to look for the density of x under the kth distribution, because that's the membership information that I've gotten. And then this is just the summing over the different k different states, but using a new dummy variable. So this is just the usual thing from Bayes there. So you'll notice that everything in all the parameters in here have t's associated with them, and I'm just going to call this guy p k I t. So this is basically the probability of being in the kth class, of the ith observation being in the kth class, given that I'm assuming basically the parameters are whatever the parameters are at this tth iteration. Okay, so this is sort of my current best sort of soft estimate of the class information for a given observation. That I sort of have a soft assignment of classes for the observations. I'm not saying for sure that that the ith observation is the key in the kth class. I'm saying that this is the probability the ith observation is in the kth class. So that's the sense in which it's a sort of soft assignment. Okay, so this is the conclusion of the expected value of the E step of the algorithm. Now we just need to go ahead and maximize, and that will give us the update that tells us what's the t plus 1th value for theta in our iterative procedure. So if I think about maximizing this, I now just have a sum over I, a sum over k, p, k, I, t. These are basically fixed. They don't involve the param. Now when I think about maximization, I have to sort of change my worldview at this point. I'm thinking about maximizing. What am I maximizing with respect to? I'm maximizing with respect to theta, which are the pi's and the mu's and the sigmas. And if I look at this expression here and think about maximizing, well, I look at sort of this expression with the pkit in there and think about maximizing that, then I have fk of xi. Well, where are the parameters in here? There aren't any parameters in here. Those are the things where those things have what's gotten plugged in there are basically the t values for the parameters. So if I think I'm maximizing this with respect to theta, well, that's maximizing with respect to that, with respect to that, with respect to that. And the other convenient thing about this is if we think about breaking this out into this and this times this as two different pieces in our sum, if I'm going to go ahead and maximize that with respect to the parameters, I can just maximize with respect to the parameters of the distribution, the normal distributions, and I can separately maximize with respect to the parameters that are the weights of the components, because this is just a summation. And so if I think about taking derivatives with respect to these, this is going to drop out when I take a derivative with respect to pi, and this is going to drop out when I take a derivative with respect to mu k and sigma k. So I can just do two separate maximization problems. Okay, questions or comments at this point? Okay, so now if I think, let's do the pi k first. So I'm going to maximize sum over I, sum over k, pk, it, log of pi k. And you could just go ahead and take a derivative with respect to the pi k's and set that to 0 and try and solve for that. But the easier thing to do is just to recognize that this actually looks like a multinomial likelihood. The problem is the sort of notation looks a little bit weird in terms of actually recognizing that. like if I think about a binomial distribution, what does a binomial distribution look like? It looks like p to the y, 1 minus p to the 1 minus y. And if I think about generalizing that to a multinomial, it looks like pk to the yk product over k. And if I take a log of that, then I get a sum over k of yk log pk. Well, now if we look here, well, okay, this looks like these are now the p's, and these are the data, the y's. So if I think about what the maximum likelihood estimator for a multinomial is, well, it's just counting up the number of observations that fell in a given class and dividing by the total number of observations, and I do that for each of the capital K different classes. Well, what do I do here? If I just work through that same logic, I'm basically just going to be summing up over the, for a given K, I'm going to be summing up pkit over the observations. So it's now not that I'm summing up the number of 1 for each observation that falls in the class, it's that I'm summing up these soft assignments for each of the classes. So maybe for one observation, pkit is 0.2, and for another it's 0.35, and so on and so forth. Whereas if in a normal multinomial situation, I would have, yes, it's either in that class or not, I would have a whole bunch of 1s and 0s. But in this case, I sum up the 1s and divide the total number of observations. In this case, I sum up the soft assignment values, these pkits, and divide by the total number of observations. So one of the reasons I wanted to go through this example in detail was just to work out EM, but another one of them was to think about be able to think about latent variables, and another is this idea of sort of soft assignment comes up in a variety of different contexts, so I think it's a nice thing to see. Okay, so that means that pi k t plus 1 is equal to a sum over I of pk it over n, just the number of observations. So this tells me how to get to the next set of pi's. All right, any questions before I do the mu k's and the sigma k's? The other nice thing about EM, when it works out this nicely, and it should in the problem set, and it does for some other problems, is you get these nice interpretations, like I was saying, with this idea of sort of soft assignment. Basically, at a given iteration, you're saying, this observation isn't totally associated with that cluster, but it's sort of this proportion associated with that cluster. And then I can sort of treat it in some ways like I would treat hard assignments. Okay. So now if I think about, I've already dealt with the log pi k times the pkit, that's part of the sum. Now I'm just going to deal with this part of the sum. Okay, so we already sort of talked through part of this. If you knew which observations were associated with the kth cluster, with the kth normal distribution, how would you estimate mu k and sigma k? You just take the average of the observations that were associated with that component, then you take the maximum likelihood estimator for the variance or for the standard deviation, and you'd be done, right? Or one of the world's more simple statistical problems. Okay, so what is this? Well, this is just summing over the observations. We have a sum over k, pk, it. If we think about, okay, so let me step back a second. Let's just think about let's just take one of the components. Let's say the kth component. So I'm going to try and find mu k t plus 1 and sigma k t plus 1. Well, this here is now a sum over I and a sum over k. So the same thing holds that when thinking about the optimization, the maximization. If I think about taking a derivative with respect to mu k and sigma k, the terms in the summation that don't involve k are going to drop out. Right? So all I have is sum over I for a given pkit times this business. So I have a sum over I for k specifically, I have pkit, and then what do I have? I have just the usual normal distribution. So I have times minus 1/2 log sigma k minus 1/2 sum of xi minus mu k squared over sigma k squared. Well, I could go ahead and take derivatives and just churn through the usual maximization, through the usual likelihood maximization here. And what you'll see is that you'll get a sort of intuitive answer, which you might have guessed if you just sort of stared at this long enough, which is, what does this look like? If I didn't have this here, this would just be a standard problem, right? These are just constants. They're not involved in the maximization. They're just constants in front of these terms. So what is this? This is just a weighted sum. So this is a weighted likelihood, or weighted log likelihood. And these are the weights. And again, there's this idea of soft assignment. Instead of saying, I know these observations are associated with that component, I say, well, this observation has a 0.8 association with that cluster, and this observation has a 0.05 association with that cluster, and this one has a 0.3 association with that cluster. Those are the weights here. So basically, all I'm doing is sort of solving a weighted likelihood, log likelihood maximization problem here. And if you work it out, you'll get sort of what you expect, which is that what you'll expect if you sort of continue with that line of logic, which is mu k t plus 1 is just a weighted average. So it's the sum over I pk it times xi, and on the denominator I just need to divide by the sum of the weights because it's just a weighted average. So I've got sum over I pk it. And you can do something similar for the sigma kt I. You just basically get what looks like a weighted variance estimator instead of the usual unweighted variance estimator. Okay, so that's all I had to say, sort of working through it. There are some details we sort of skipped over a little bit, but I think now that you've seen this, if you went back to them, you should be able to sort of work through those pieces. And I'm happy to take any questions now, and I'm also obviously in the office hour. Jared or I are happy to, if you want to work through this in more detail, and if there are pieces that you're confused about, you can ask us then. But are there any questions before I move along here? Okay. So I think for me, whenever I'm doing this, the main thing that sort of trips me up is this idea that when I'm at this step, I'm taking an expected value, I'm figuring out that this is the random thing and that the expected value is taking the parameter values to be the theta sub t's and leaving these guys alone. Don't ever change these guys, the thetas that are in the problem here. And then when I get to the maximization step, realizing that any place I have parameters with a t on them, like here, they're just constants. I leave those guys alone, and I'm maximizing with respect to this guy, these guys, those guys there. So if you can sort of make sure you keep those two things straight, I think it becomes a lot more straightforward. And if in your derivation on the problem set, obviously you wouldn't know this if you were doing this for real on a problem that you hadn't seen before and hadn't already been solved by somebody else. If you get to the point when you're doing it on your problem set and you're getting something really ugly that doesn't simplify down to something that's interpretable in sort of the way that we saw with soft assignments here, that means you've probably gone a step in the wrong direction in some way, because it should sort of work out really nicely, basically. Okay, so that was EM. You can well, I guess I'll go back and I'll say a few more things about EM in context in a minute. Okay, so the idea of this section was we're going to be thinking about optimizing convex functions. And this is sort of a huge topic. There are whole classes taught on convex optimization, so we're really just going to skim the very surface of this. But I want to give you sort of a sense for what goes on here and when you might have a problem that involves convex optimization. Okay, so the reason why doing convex optimization is nice is because if you have a convex function that you're trying to find the minimum of, there's only one minimum, and it is the global minimum. And so if you know that you're in that setting, things like Newton's method are going to work really well because you don't have to worry about things like that we saw where things were diverging off in the wrong direction. You don't have to worry about inflection points in the function, and all those complexities go away. And there are algorithms that exist for solving convex optimization problems that are well established. So if you can figure out that you have a convex optimization problem, then you can usually just employ that machinery. Okay, so what is convex optimization? Or what is a convex problem? Okay, so the idea is that we're optimizing on some convex set. So if we have, we're trying to find the best x within some set. So suppose our set looked like this. Sorry, I don't want to draw wiggles like that. Trying to draw this as convex without drawing it just as a circle. But so basically, a convex set is if you can take 2 points on the edge and you connect the line that all the points between those 2 points are inside the set as opposed to outside. So if you had something that had sort of wiggles like this is not convex because you've got these 2 points here, you draw a line through it, and these points here are not inside the shape there. Okay, so then the idea is if you're optimizing over x in a convex set that looks like this, then you also need that your function is convex. So what does that mean? Well, everybody's seen, I think, concave convex functions. But there are a few ways of thinking about this that are useful to think about that help in terms of intuition. So if I have a function that's convex, well, one thing it means is that if I take 2 points along that function and then connect them, that between those 2 points, the line is above the function, right? So that means it's convex. Another way of thinking about it is that if I were to draw the tangent line at any given point, the tangent line is always below or at that point equal to the function. So the tangent's always below the convex function. And the other is basically that the second derivative is always increasing. So in this one-dimensional case, that f prime of x is always greater than 0. And in the higher dimensional case, that the Hessian is positive definite. Okay, so basically any direction if we think about the second derivative in any direction, that thing is increasing. So that's what the positive definiteness means. Okay, and just to sort of hit back on a point that I was trying to make before, which is this idea of sort of why are these functions nice to optimize? Well, think about where things went wrong with Newton's method. Right? Things with Newton's methods went wrong, for example, if we had that the function had an inflection point and started to sort of turn over. And in that case, we could see if we started out here, that Newton's method might go off sort of in this direction as opposed to going towards this local minimum. Right? But if the function's convex, that's never going to happen, basically because the gradient is always getting steeper and steeper and steeper. So we always have it sort of going up like that. And so what that means is basically methods are always going to be able to go and zero in on the minimum. All right. Let's see. Any questions so far? Okay. So if you had an optimization problem and you wanted to figure out if it was a convex optimization, there are all sorts of results that allow us to determine if this set of operations on a function preserves convexity, and so you could sort of try and work through the details of whether or not you had a convex function or not. That's sort of beyond the scope of what we can cover here. But the name of the game is basically try and be able to recognize and prove that the given function that you're optimizing is convex. Okay, so let's talk a little bit about some methods for working with convex functions. So one of them is kind of this cute algorithm called the MM algorithm, which stands for either maximize, minorize, or minorize, maximize, or major. Let's see, what is it exactly? I must have written it here. Majorize, minorize, sorry. There are too many M's floating around. So what's the idea of MM? And it turns out that the EM algorithm that we just saw is actually a special case of the MM algorithm. And so that's partly why I wanted to mention this MM algorithm. But the idea of the MM algorithm is if you have a convex function like this, then I should be able to construct what's called a majorizing function that will touch this function and then basically always be above it. So what the idea is, if this is theta sub t, so again, this is going to be an iterative algorithm, right? So if I'm at theta sub t here, I guess maybe I should call it x. Yeah, sorry, let me call it x sub t. If I'm at x sub t here, I basically construct, if I can figure out how to do this, I would construct this function here, and the idea is this function is going to touch the function I'm interested in at that point, and otherwise it's always going to be above the function. And so the idea is if I can construct one of these that's easy to minimize with respect to, then what I'll do is I'll actually minimize with respect to this function and move downhill with respect to this function. And let's suppose that I move down here to this point. Well, moving downhill with respect to this point, this function is going to be is not going to give us any problems with respect to moving downhill with respect to this function because this one's always above that one. And so, okay, so I get to this point. Now I have my new value x sub t plus 1 here. I construct a new majorizing function. I walk down that function to find the new function, and eventually I just walk my way down by virtue of optimizing in terms of these approximating sort of upper bound functions. So that's the main thing. It's sort of a meta algorithm because I've sort of told you what the algorithm is, but in any particular problem, the hard part is actually figuring out what this function is going to be. So I haven't actually told you very much at all in some ways. But the idea is, since we're trying to find this majorizing function, we want to find something. Basically, you need to work with inequalities to make sure that this thing is going to be above the function that you're trying to optimize. And so that involves getting some facility with working with inequalities. Okay, so so it turns out that EM, remember when we were doing EM, we were maximizing as opposed to minimizing. We were maximizing the log likelihood. I never took a negative of the function to get to the negative log likelihood. So it turns out that what EM is doing is basically doing the sort of the reverse of this. That if you think of the log likelihood for EM, where we have the log likelihood being f of x given theta, then basically what happens by constructing that expected log likelihood, we're basically constructing an approximation that is below the thing that we're trying to optimize. At a given iteration, we maximize with respect to this, and we move uphill, and then that gives us the next step, and we continue onward. So it's basically this same thing, except maximizing instead of minimizing. Okay, so in terms of an example, there's sort of a nice little example for solving a least absolute deviation regression instead of a least squares regression. So suppose the problem I was trying to solve was that my objective function, probably should call it f because I was using that as my likelihood, as my density function. Let me just call this thing h. Okay, so suppose instead of regressing y on some covariance z using the usual regression machinery, I'm going to use z because I've got x over here, so I'm trying to use different notation. Suppose I have covariance z and I have observations y, but instead of minimizing the sum of squares, I decide to minimize the sum of the absolute deviations. Okay, so I'm trying to I'm trying to do a robust regression where I don't have that strong influence of very large residuals because they get squared. So instead, I've got the absolute residuals. So if you look at this and start to try and maximize it, you're like, oh my god, I have to deal with absolute values, and that's always difficult to deal with when you're doing optimization. So the trick for using an MM algorithm in this case is to basically work with a transformed version of this problem. So I'm going to write this out as the sum over I of Ri of theta squared root. So this is the same thing. I'm just saying take the square root where I'm taking the positive square root. So I'm just squaring these and then taking the square root to make sure I've got a positive value. So I'm just defining this as Ri of theta. So these are just the residuals. And now the trick is to work with inequalities. So it turns out that if I have I have a concave function, so suppose I have a function that looks like this, and the concave function that I'm particularly going to interested in is the square root function, which would look something like this shape here. Then I can write that down as, I can write down an inequality for here that says g of x is less than or equal to g of y plus g prime of y times x minus y. So what is this doing? This is just saying that at some, if I want to come up with an upper bound for g of x, and this is g of x, I can pick some point y, I can basically do the Taylor series linear approximation to that function here, and this function is always going to be above the function of interest. Okay. So if we use this inequality with the square root function and work out what the derivative of the square root function is, I'm not going to go through it in detail, but that would be easy enough for you guys to do on your own. We'll see that my objective function is less than or equal to the sum over I of the square root of Ri of theta sub t squared. So the value y that I'm trying to do my approximation around is that I'm going to take it to be the theta at the t iteration. So the theta at whatever my current iteration is, and I'm going to be deriving what theta t plus 1 is, and it's sort of the usual thing that we've been doing. And I can write this out as plus Ri of theta squared minus Ri of theta t squared over 2 square root Ri of theta t squared. Okay, so that just comes from working through this with the square root as the particular concave function that I'm focused on. Okay, so actually questions at this point? Okay. So what I might notice here is if I think about this part of the expression here, that's just something over the square root of that same something. And that's going to basically give me another term like this. So if I just rearrange terms, what I'll get is that this is equal to the sum over I of 1/2 square root of Ri of theta t squared plus Ri of theta squared over 2 square root Ri of theta t squared. Okay, so just combine terms there. And now we sort of do something like what we did with the EM problem, where if we sort of have our wits about us enough to sort of stare at this for a little bit and think about what we're doing here. What have I done so far? Actually, I sort of got into that track a little bit more quickly than I meant to. Before I sort of say let's sort of stare at this and think about how we can maximize this, let me go back and make clear that we've now derived our upper bound. Okay, so over here I said I was trying to find this function that could serve as an upper bound of my objective function, right? So I've now found that thing. That's what the less than is giving me. Okay, so that gave me this. And now I need to maximize with respect to that upper bound function. So now I've got this function, and I'm going to maximize with respect to it. Minimize with respect to it to go downhill. Okay, so now I know. Okay, so now I know I need to maximize this. The same thing we saw with EM. What am I maximizing with respect to? At this point, everything that has a theta t in it is just a constant. It's just going to be a number. I can just plug in whatever the current theta t is. I can plug in the current theta t, come up with the current values of the residuals, and they're just numbers. They're based on my data, and they're based on theta t. So what am I doing here? Well, I'm going to maximize this thing with respect to theta. This is just a constant. If I maximize with respect to theta, it just falls out. Right? So what am I doing? I'm maximizing with respect to theta this thing. Well, what's this thing in the numerator? If I didn't have the denominator, what problem am I solving here? Ordinary squares, right? This is just the sum of squared deviations, sum of squared residuals. So now these are just numbers. So what is this? This is just a weighted least squares problem. And I'm just trying to minimize the sum of squared deviations, except each of those observations has a weight associated with it, which is, depending on whether I define the weight to be the thing in the denominator or 1 over that thing, but it's a weighted least squares problem. So I guess we didn't do that problem on the problem set this year, but if you think about what a weighted least squares problem looks like, I think we've actually seen this before. The solution to that is this. That's well known. That'll be in any textbook that talks about weighted or generalized least squares. In this case, the sigma, instead of being a general matrix, is just going to be a diagonal matrix where the diagonals involve the weights. But either way, it has a well-known solution. Okay, so we just solved the weighted least squares problem for this. We get theta t plus 1, then we go back and plug in theta t plus 1 to get our new upper bound, and we repeat and continually do the minimization of this objective function. Okay, questions or comments about that?
So I'm a little bit confused by what the benefits of using this algorithm. So suppose we have a convex function already. Why not just using the gradient descent for the local or global?
Yeah, so that's a really good question. That's not to say that we couldn't, for example, use, say, a Newton-like method in this particular problem. We could also do that. It's just a matter of, it might be that, well, a couple things. I guess one is this might converge faster than doing Newton's method. It's not, we wouldn't know, I guess, unless we tried it, although Newton's method presumably should converge fairly quickly. The other thing is that in cases like this where it works out quite nicely, you could just use standard machinery to do weighted least squares to solve that problem, as opposed to having to run Newton's method in this problem. So, yeah, I don't actually know in this case whether.
But that is still an iterative process, right?
Yeah, both of them involve iterations. So, yeah, so it's a good question. I don't actually know whether this would be. Whether it be an advantage to doing this for this using the MM algorithm for this particular problem. It's sort of like if we are fitting a generalized linear model, we know that iteratively reweighted least squares is sort of the standard algorithm, but you could just employ an off-the-shelf optimization algorithm to find that to minimize that objective function. So you could use either. Yeah, I feel like I should have a better answer for that question because I think it's a good one, but I don't have a particularly good answer off the top of my head. Okay, other questions? Okay, so that was MM. EM I mentioned is a special case of MM. Okay, so now let's start talking about optimizing under constraints, and this will basically take us, well, obviously through the rest of today, but this will basically take us through Wednesday and through the end of the unit. Okay, so the idea is in lots of statistical problems, you are often in the situation of trying to minimize some objective function, say minimize some negative log likelihood, but you may be doing it in the context of having some constraints. And those constraints will come up in, for example, dealing with sparse regression problems like the lasso kind of, that sometimes comes up with a lasso-like problem, or other kinds of problems like that. So particularly in the last 10 years, there have been a lot of statistical methods that finding the parameter estimates involves a constrained optimization problem. And oftentimes they can be written as one of these convex optimization problems. Okay, so you'll often hear the word programming, which I'm sure those of you in the operations research program have heard a lot. But basically, I think my understanding is that when you optimize under constraints, one name for that is programming. So you'll hear things like linear programming and quadratic programming and cone programming, second-order cone programming, and things like that. And all of those involve different kinds of optimization problems where there's a constraint involved. So we'll see a couple examples of that. But the more general problem is if you're doing convex optimization with these constraints, then it's often called convex programming. So you may also hear that terminology. Okay, so the idea of what convex programming is you have some f of x that you want to minimize, but then you have a whole set of constraints that you're needing to respect. And those might be equality constraints. So you might have some set of linear constraints on the x's. So this would be a set of coefficients. So for i equals 1, I have a1, so that's just a set of numbers, a1 up through a, however many of the x's there are, that when multiplied by x, the inner product of that is just some constraint value bi. So you might have a set of these Q linear constraints, and then you might also have inequality constraints. So you might have a constraint that some h sub j function of x is, say, less than or equal to 0. Okay, so if I take some nonlinear function of the x's, that has to be, say, less than 0. So if it's the case that f is convex and these h inequality constraint functions are also convex, then we have a convex programming problem. And the other thing I'll note here is it might look kind of restrictive how I've written this here, like I've written less than or equal to 0. And just I don't have a greater than, for example, here, and I have a 0 here instead of some more general value on the right-hand side of this inequality. But you can also think of basically rewriting things. Like if I had a nonlinear g of x is equal to b, I could write that out as two constraints with a less than inequality and a greater than inequality. And if I had a greater than bj, I could write it out. I could take the minus of that, and I could always subtract off. If I wanted to have this be less than or equal to some number, I can always subtract that number from both sides and make sure I have a 0 on the right-hand side. So if you're looking at methods for dealing with convex optimization, you'll often see people say, oh, you have to write your constraints in this particular form, and you might have to do a little bit of this sort of manipulation. Okay, but the idea is that you would get it into that form, and then you would then go through and then there may very well be software that would then allow you to, there is software that would then allow you to solve that convex programming problem. Okay, so oftentimes you can actually do this pretty well with hundreds or even thousands or more of variables if you can figure out that it's a convex programming problem. And so that's sort of the big picture here. So I thought what I would do next is I'll talk about a few specific examples. I'll just cover one now, and then we'll see a few more on Wednesday, and then we'll also we'll just see the basic software in R for doing constrained optimization, so you can get a sense for it in practice as well. Okay, so suppose that we have a much simpler system than what I set up here. So up here I said, okay, suppose we have some arbitrary f that's convex, and these inequalities where the h's are convex, and then we have these set of linear equality constraints. Well, what if instead we had a simpler problem where we had f was just a linear function? So f is just c1 times x1 plus c2 times x2 plus c up to cq up to xq, how q is however many, whatever the dimension of x is. And now suppose I have m of these constraint functions that ai, the row ai times inner product times x is less than or equal to bi. So the question is, how would I solve that problem? And see if I have my picture here. So this is a linear programming problem. And if we think about what's going on, and I think about the constraints, well, basically each of those AI transpose XB constraints is basically just going to be a hyperplane. I have to be basically under that hyperplane if I have it as less than or equal. So one way I could think about that is, suppose that I were in 2 dimensions. I could think about those constraints basically forming a sort of polygon, and the only valid potential solutions, the only valid potential x's lie within here. So this might be, say, A1 transpose x is less than, well, I guess the line itself would be equals to B1. And this would be A2 transpose x is equal to B2, and so on and so forth. And now if I think about, okay, now I think about my function f. My function f is just a linear function. So if I think about it, well, it's just a hyperplane, the function, this c times x function. So if I were to be sitting here in 2 dimensions and think about that, I've got some plane here, and I'm trying to optimize with respect to that plane. If there are no constraints, what happens? Right? I would just keep following that plane uphill on off to infinity, And if there are no constraints, I'm just going to keep going in whatever that direction is. That's the gradient of that plane going uphill in that plane. So if I now think about the fact that there are constraints, what has to happen is if my plane sort of looks like this, I'm going to go uphill on it until I hit one of these constraints. And then I'm either going to go in one direction or the other to sort of keep going uphill. And so basically what has to happen is that the optimum has to lie at one of these vertices. Okay, because I'm basically going to sort of go uphill, and then I'm going to sort of keep going uphill until I get to here. And at this point, I can't go uphill anymore and still respect all the constraints. So that's sort of the sort of big picture name of the game if you're doing this kind of if you've got this linear function and these linear constraints, except you could be in a much higher dimensional space in which you're doing this, in which you're working this out. So I'm not going to say anything more about that except just so you have the feel of it, the feel for it. And there's something called the, let's see, so yeah, so basically any algorithm would basically have to do this. You'd have to, if you ended up sort of move to one of the constraint functions, and then you'd sort of keep walking, have to keep going uphill until you got to the right vertex. And there's something called the simplex algorithm, which actually starts with what's called the feasible solution. And we'll see this word feasible in other contexts. So basically, a feasible solution is any one is something that is a set of the x values that satisfy the constraints. That's feasible. It's not necessarily the optimum, but it satisfies the constraints, so it's one that we can consider. So the idea of the simplex is that you're basically starting at one of these corners, and then it basically figures out how to get to the correct vertex. Okay, so I think that's all I want to say about that. Any questions or comments? Yeah.
Can you give a 30-second rundown of this inequality notation that you introduced?
Yeah, sorry, I should have said that before. I think I have that somewhere here. Yeah, so the idea is that I have a system of inequalities here, one for as I index over I. So I've got A1x less than or equal to B1, A2x less than or equal to B2. So all that this notation means is I'm going to put all of the A vectors in as rows. I'm going to put all the B's so all the A vectors, all of the AI vectors as rows of this matrix A, and all of the B elements as elements of the vector B. And then this funny business here just means I'm satisfying less than or equal to for all of those sets of things. Okay, other questions? Okay, so next time we will see some more general cases, including quadratic programming, and a little bit about something called the KKT conditions for optimality, and then constrained optimization in R. Yeah.
Hey guys. I have an announcement for the MA students in the stats program. If you're not in the program, feel free to continue packing up. Don't worry, I won't be offended. Basically, I wanted to make a